You know that? Yeah, I think so. She can just like take it. Also the property that somebody like Martin's on this ring.
Ooh.
That's
That's rough.
All right. Does anybody have any questions about the homework? Yes?
Could you go over 3.7c from the homework?
Sure. We're going to go through properties today of the Laplace transform. That makes it all easy. The Laplace transforms are they're things that you can brute force almost any problem. But by God, the properties make solving it so much easier. So we're going to go through that. 3 point. Which one was it?
3.7c.
Oh, okay. Let me just say this. I think we can get to that if we do properties first, all
Okay.
right? Because I'm going to tell you there's a couple of tricks with that one. That's the 1 over t sine of omega naught t. And that's we times u of t. That's a trick problem. First, with Laplace transforms in general, remember the fundamental definition. I'm going to write it over here and just leave it up. I know that x of s of a function is equal to the integral from 0 to infinity of x of t times e to the minus st dt. We know s is sigma plus j omega. That's the fundamental definition. That marker is just about out of juice. So, now, today, what I want to do, before I do these, because the properties make it easy to do, I'm going to go through the properties. Now, you can always, when I say brute force, I mean whatever the function x of t is, if you put it in here, you can do that integral. The problem is, sometimes it's a long, painstaking thing. Your calculators do symbolic integration to a point. They don't do symbolic integration of really bizarre functions. Now, if you have access to Wolfram Alpha on your phone, it probably will do a larger class. But some of these get really tricky, especially if they have things called Bessel functions or Legendre polynomials, functions that are not real common to everybody's usage. All right? So just be careful. The properties will let you do it in a very easy way. So when I say properties, what do I mean? Well, first one is linearity. It means if you have some constant a times x of t plus some constant, call it x1, b plus x2 of t, and you want to know this is going to be the function f of t, and this is the transform f of s. You want to know the transform of that? Well, it is just a times x1 of s plus b times x2 of s. What that means is there's a linear operation. So if you want the transform of like e to the minus 10t u of t and a delta function, right? And they're added together. You just take the transform of e to the minus 10t u of t, which is 1 over s plus 10, and the transform of a delta function, which is 1, and add them together, and that's it. You got me on that one? That's linearity. It's self-evident. The second one is time scaling. This one happens all the time. So if we have a function x of at, and we want to know what it goes to, I'm going to put it down and prove it. It goes to 1 over a, x of s over a. And here's how come it does that. It's important to know why things do what they do. And I'm going to do that one over here. So if you have the fundamental definition over there to look at, I know if I have the integral of x of at times e to the minus st dt from 0 to infinity, you all agree that's the Laplace transform of that function. I want to know what it is. What you do is create a variable u equal to at, and then du equals a dt. You all see what I'm doing? I'm simply going ahead and I'm doing a variable transform. Now when I do that, Can y'all see it over here on that side? Okay. Now what I do is I plug this stuff in there and I get the integral of x of u e to the minus s, but not t, but u over a. So I'm going to put s over a times t, and then dt becomes du over a. And the limits are still 0 to infinity. Does everybody see how I just did the exchange? I substituted it for t, I substituted in u over a, and for dt, I du over a, right? Now, if you look at this carefully, the 1 over a can come out in front as such. I think you all see that. And when I look at this, well, this is the definition of the Laplace transform, but instead of quote s, now our variable we're transforming is s over a. Does everybody see that? And therefore this is equated to simply 1 over a x of s over a. And it doesn't matter what a is. It doesn't. It could be a real, it could be imaginary, it could be a complex number, it doesn't matter. So that's this property, that's time scaling. The next property, I've got a lot of, this is just a time shift. If you know, and this assumes one thing, we're assuming we know that x of t goes to x of s. We know that transform pair. For instance, if it was a delta function here, it would go to 1. All right? We're saying if we know that, then these properties all apply. So the next function is this. If I have, this is going to be a standard time shift. If I have x of t minus a times u of t minus a, and I want to know what happens over here, I go to the definition of the Laplace transform, and I'll do it right over here. And I can say, well, it's the integral of x of t minus a, u of t minus a, times e to the minus st dt. That's the definition, fundamental, right? Correct, class? Mm-hmm. Now, you get used to doing this in the beginning. Just writing this over and over again, it'll stay with you. You'll never forget it. But if you, when you try cramming, especially at the end, towards the ends of this course, you're going to have a whole bunch of different things in your head. If you try cramming, you're going to get confused. But if you just learn it on the fly, like just get it, you won't. All right, now for this one, the trick is this. Everything's 0 until this u function turns on, right? It turns on at a. So what I do is just erase it and just make this a. Okay? And now we do a variable transform just as before. We allow u to be equal to t minus a, and then du is dt, correct, class? Now, at that point, the only thing we do is make the proper substitutions, and I'm going to substitute it right there, okay? So now I can say that this is x of u, right? T becomes u plus a, doesn't it, class? Do y'all see that? So this becomes u plus a, and dt becomes du. You can all see that it's just a straightforward matter. Yes?
When you did the other one, wouldn't t be u divided by a?
It is. I took 1 over a in front.
Oh.
Okay. I had it in there, but I moved that out in front so you could see the Laplace, the clear definition of the Laplace transform by itself. Now, here, when you look at this, I can break this up in e to the minus su times e to the minus sa. Correct, class? You'll notice the integral is with u, so I can take e to the minus sa out in front. And what do you think of that is that I'm boxing right there? Well, and by the way, the lower limit is, since it is in t, but t becomes u minus a, it actually goes from 0 there. I'm sorry I didn't change that one too, all right? So what happens? Remember, t is u plus a. The lower limit was a, now it's plus, it goes down to, it's basically starts at 0. You see how this is the definition of Laplace transform, everybody? So that means this right here, and this is called a phase shift. This is simply e to the minus sa times the actual transform, x of s. Please understand this. we're going to spend more time with the Laplace transforms. Whenever you do a time shift of when the function starts, the form of the Laplace transform is the same, basic shape of it. The thing is, you get a phase change out in front. You get that e to the minus as. And when s is strictly real, when s is strictly imaginary, j omega, this is just a phase change. And I'll get to that a lot more later. But this is something, the standard form remains the same. There's just this phase operator in front of it. This one you have to know. These properties you have to know. You have to know them well too. Next thing I'm going to do, I want to do the sine and the cosine separately, even though it's not a true transform, because we use those so often. I want to do it. All right. Let me do one more before I do the sine cosine though. There's one property. These are all properties. If I have e to the minus at times x of t, and I want the transform of that. Now remember, it assumes we know x of t goes to x of s in here. Then this is another thing that happens all the time. You have these exponentials, damped exponentials, multiplying sines, cosines, things like that. They happen everywhere. So just remember, this is a common form. That's the reason I'm putting up the property. Well, what it does is this. Let me go up here and do it. I'm trying to put the properties there. If you have e to the minus at x of t times e to the minus st dt integrated from 0 to infinity, that is the Laplace transform of e to the minus at x of t, right? Now, here's what we're going to do. We're going to group the exponentials together. Follow me on that? And when I do that, I get this. I get the integral from 0 to infinity of x of t, and then I get e to the minus quantity s plus a t dt. Do y'all follow me? I just put the exponentials grouped. Now this is important. When I do this definition here, what you have to appreciate is s is the only thing that comes over here as the argument. Got me? The integration takes place, and this is only a function of s. Now it doesn't have to be s. It could be u. This is just the transform operator. It doesn't matter what that symbol is. Do you understand me? It could be u plus 10. It doesn't matter. Whatever that transform operator is, it goes right here. Now, that means when I look at this, this is really equal to simply x of s plus a. You all see that? Right? That transform operator is s plus a multiplying t. Do you all see that? There's a negative sign in front of it. You just take that and put it over here. So now you get x of s plus a, which is nice. Makes life easy, in a sense. And these properties are things I pray that you use these. I hope you do. And I'd recommend you do like 20, 30 problems this weekend where you're applying the properties and just seeing if you get the right answer. Something else I'll tell you. How many know what Wolfram alpha is? All right. How many know what MATLAB is? All right. You should have all been exposed to MATLAB by this time. MATLAB does symbolic integration, and it does symbolic Laplace transforms. Wolfram alpha does that. If you're using Mathematica, it does that. There are many other tools that will give you the actual Laplace transform of just about anything. So if you're ever wondering what the answer is, you can always get on one of these tools and just put in the function that's driving you nuts, like the one that you asked me about. Did you do this on Wolfram alpha, by the way?
No, I use the tables mostly.
Okay, yeah. That's what you should do, is rely on the book. But if you just want the answer to see if you got it, you can get it through these tools. If I have time, I'll show you this. And I'm going to tell you another thing. Now, when I was sitting where you are a long time ago, we didn't have the internet, we didn't have anything like that. But we did have an immense amount of tabulated forms of Laplace transform for about anything. Matter of fact, I had a book, and I don't have the book, but it was by Comke, it was in German, and it had the solution, general solution to every differential equation, linear up to fifth order. And it had any form you could imagine, you could find it. You know, that was a godsend. When you're doing especially higher level courses, everything is described in terms of differential equations, and you need the general solution, and then the boundary conditions is what you fit to the form. All right. So now we do the sine and cosine. I'll start with the cosine form. This is an important one. So if you have cosine of omega naught t u of t, the u of t, make sure it starts at t equals 0. And you want to know what the transform is of that. And what you're going to see is, I'm going to work it right here. I'm going to put two other things up you have to know. You have to know these. I mentioned it before. You have to know cosine of omega naught t is equal to e to the j omega naught t plus e to the minus j omega naught t over 2. And you have to know sine of omega naught t is equal to e to the j omega naught t minus e to the minus j omega naught t over 2j. And one more, you should know e to the j omega naught t is equal to cosine of omega naught t plus j sine of omega naught t. You all have seen them before, right? This is stuff in circuits you probably saw over and over again, some form of this. I don't remember which one Dave Rowan uses if you had him, but I know I made sure they knew them all. This is just standard Euler's identity. It's spelled E-U-L, all right, not O-I. Euler's identity, it's pronounced Euler's. Now, when you think about, I'm going to put this up here, but I'm going to actually do a sidebar on this and show you something about that, why it's important. Anytime you see e to the j theta, what you're really doing is talking about something in the complex plane where that's the real axis and this is the imaginary axis or j-axis. And you have a vector here of length 1 and it's rotating this direction. And the angle right here is theta. You understand that? So the vector has length 1 and it's rotating as theta increases in value. It's going counterclockwise. You all see what I'm talking about? It's like a hand on a clock. Now the projection of this on the real axis would be the cosine of that angle. So this is cosine of theta. And the projection on the imaginary axis would be sine of theta. And therefore, cosine theta plus j sine theta is e to the j theta. Do you all follow me on this? That's the way you can remember it. You can get any of the expressions from there. When I talk about the function for the cosine, if you take a look at this, well, if I have this right here, I also have something that looks like this. Would have the angle theta, this would be a cosine theta again, right? Correct, class? And then if you took the actual, and just have that value, you would get the proper value for cosine theta. Now, why am I saying this? Because if you look at this, what did I just do? Well, here is e to the j theta, right? Okay. If I divide that by 2, I have this, and that would be 1/2, correct? Now, what is e to the minus j theta? Well, that's this, isn't it? And let's divide that by 2, right? Add them up tip to tail. What do you get? You get this. And what is that? Is the cosine of, because then now both of those links are 1, right? It's the cosine of theta. You see that expression for cosine of theta? That's how you get these. It's always from that drawing. You can work on this later, but you should at least be exposed to this. I don't know how you were exposed to it. Usually they do this e to the j theta, and they talk about how you get the cosine, the sine. You can get tan, you can get all sorts of things if you really want them from there, in terms of e to the j theta. All right, now back to this, cosine. So what I'm going to do for this transform, I'm going to replace cosine with the exponential Euler's version of that, okay? So now I say, well, the Laplace transform is the integral from 0 to infinity of 1/2 that I'll take outside, and then it's going to be e to the j omega t, or omega naught t, plus e to the minus j omega naught t, and it's times e to the minus st dt. Does everybody agree with that? Class, see? Now, when I'm doing this, what happens? Well, what I can do is this times this, and then break them out. Now watch. That means this thing will become 1/2 the integral from 0 to infinity of e to the minus quantity s minus j omega naught times t dt. And then it's going to be plus 1/2 I'll get out of your way in a second. E to the minus quantity s plus j omega naught t dt. You can see what I've done. I've simply combined the exponential terms, and now I look at this right here. And here I want to just slow down for a moment, make sure you see this. First, think of the fundamental definition, right? I'll replace this with the s. Whatever that variable is that's multiplying t, as long as there's an x of t here and t here, and t could be any variable too, right? T is integrated out. But whatever is next to that t is the transform variable. You all follow me? Now, when you come here, what's the transform variable? S minus j omega, right? How many can see that the transform variable here is s plus j omega? So that means this is equal to 1/2. Actually, let me go a step further. I should have said this. If I just have, if I just do the integration on this, we can do brute force this one. I'm going to just do it and show you. When I do this integration, that's a simple integration, e to the minus a t dt, right? This s minus j omega is a constant. You follow me? dt. So what is that going to be? That will end up being just 1 over s minus j omega naught. Now, if you go through it, you're going to have a minus in front of here, and then you have to evaluate e to the minus s minus j omega naught t from 0 to infinity, but it ends up being this. That's the net result of the integration. The next one is going to be plus 1 over s plus j omega naught. Now, when you do this, and I think you're going to see this one. Everybody see what I've done so far? It's just straightforward integration, right? Now, what I want to do is get a common denominator. So I multiply this by this, right? And I end up getting the 1/2 will be there. Let me put it up higher. When I do that, I'll put the 1/2 up here. Now when I do the multiplication downstairs, I'm going to have s squared plus omega naught squared. And here's why. When I take s times s, I get s squared, right? Then when I have s times plus j omega naught, s times minus j omega naught, they cancel. You're finally left with j omega naught minus j omega naught times j omega naught. Well, the omega naughts make it omega naught squared. Minus j times j is 1. All right? Now on top over here, right, you're going to get s plus j omega naught. And then over here, when you cross multiply, you're going to get s minus j omega naught. And you can see that the j omega naughts cancel, correct, class? And you're left with s, 2s, but you got a half makes it s. It means the entire transform is simply going to be s over s squared plus omega naught squared. Do you follow me on that, class? Now that's a very important one that you need to know. All right, you have to know these. That's the first. The second one I'm going to do is when you do the actual sign. You can almost guess what happens. Right? We're going to use the Euler identity I put over there, correct, class? And the only thing and by the way, you know, this is one of these tricks I've learned I'm going to share with you. Anytime you have a cosine or a sine, and you're multiplying by some wacko function, and you want to do the integration. Now, in today's age, you probably just use Wolfram alpha. But if you break this thing up, the cosine and the sine to exponentials, usually those integrals become very easy. At most, integration by parts. All right, so I'm just telling you, that's a trick. I use it all the time. And I don't remember the identities of like cosine 2 theta and stuff. I just put it in that form, and I can get anything I want, pretty much. Anyway, when I do the sine, what's the difference? If you look at the sine form, there's a 2j, isn't there? Instead of just 2, take a look. Right? Convince yourself. Agree, class? Look at sine theta. It's what? It's e to the j theta minus e to the minus j theta, or j omega t, divided by 2j, not 2, right? So there's a 2j here. And there's also what? This becomes a minus, correct? Same exact form as before, except for those little switches. So what does that mean? Well, first of all, out in front, I'm going to have 1 over 2j. Now, you all see I'm going to combine this and this exponential. I'm going to have e to the minus s, right? S minus j omega naught times t dt. Do the integration, you get this. Just as before, you're going to get s minus j omega naught, but now instead of a plus, you get minus 1 over s plus j omega naught. I'm going to stop for a second. You all understand what I've done there, class? Give me a show of hands if you do, so I can tell. All right. Now, what I'm trying to show you is that these are simple integrations that you don't need to do them again and again. See how you do them, all right? And then just the results over here will stick with you. Now, what is this going to be? Well, I'm going to get a common denominator, correct? I'm going to multiply. First, the common denominator is going to be this times this, right? And then I have to take this upstairs here and this upstairs here, and I'm left with 1 over 2j. And then my common denominator is s squared plus omega naught squared. Over here, it's s plus j omega naught. But then it's minus the quantity s minus j omega naught. You all see that? What happens there? Well, you see the s's cancel, don't they, on top? This s gets whacked by that, right? And then the j omega naughts are multiplied by 2. I have 2j omega naught, but it's divided by j. So it gets rid of the j's, and I'm left with this. Sine of omega naught t, u of t, goes to almost the same exact form, except not s, but omega naught over s squared plus omega naught squared. Got me on that? So, gotta know sine and cosine. More properties. I did the exponential. I'm going to do differentiation. There are these properties in the book. You should work through them at least once, though. And use them. Next property is differentiation. So what happens if I have dx dt of t, and I want to know the transform of this? All right, now we go to the definition of it. When I take a look at the definition of the transform of that, the Laplace transform would be the integral from 0 to infinity of dx dt e to the minus st dt, correct? And you remember your u dv business, right? Integration by parts. You know, when you have the differential of u times v, that's equal to u dv plus v du, right? Do y'all remember doing these things? They might have used different symbols. It doesn't really matter which one. Well, if you say you've got u dv and you want to know what it equals to, it would be equal to the differential of uv minus v du. That would be u dv. Now we come over here and we say that dv is really equal to dx dt, and that's going to be my dv dx dt, I guess dt, and then u is equal to e to the minus st. All right, you remember doing this integration by parts. I don't know who taught you, but the key to integration by parts is you want to get the derivative, right? And that's this, the x dt, as the differential d, as the dv part, all right? Then whatever's left, you put in there with u, all right? And it can be 3 or 4 functions, it doesn't matter. Now what happens here is, I need to get what v is right here. Well, if that's dx dt is dv, then v itself is just x, right? X of t, correct, class? Because you integrate. And then what is du? Well, that's minus s times e to the minus st. And now you're ready to rock and roll in a sense, as they say. I had a really good prof for some of these courses, and I was so thankful. Because he really showed you all the tricks. Some don't. Some just basically this mechanical thing. He'll show you PowerPoints. That's it. When I come down here, this is my dv, this is my u. So now I have to take the differential of uv, right there. And that's going to be, what I have is this is equal to the differential of u is e to the minus st. And v is x of t, right? That's it. And then I have to subtract from that v to u, and that's x of t times, with a minus times s, times e to the minus st. So that's just the differential, right? Correct, class? Now I have to integrate them from 0 to infinity. So I integrate this from 0 to infinity, and I integrate this from 0 to infinity, correct? And when I do this, well, this is going to be e to the minus st times x of t, evaluated from 0 to infinity, plus, and this is just s, times the integral from 0 to infinity of x of t e to the minus st, and I forgot the dt here. You have to do the integration with dt. You all follow me on this? Now, I want to just make mention of this. When I look at this right here, what is this? That's the definition of the Laplace transform, isn't it? So I can just come down and say the next step is going to have just s times x of s. Now what about this one when you do the evaluation? The evaluation is key. When I evaluate it at infinity, e to the minus infinity, right? There's going to be a thing called a region of convergence, but don't worry about that now. That's 0. Now, minus at 0, well, e to the 0 is 1, and this is just going to be x. And in the book, he's going to put 0 minus. It's the value, the very first value of the time function that it takes, all right? If it starts at 0, whatever that value is. So that means this transform is simply s times x of s plus x of 0 minus. And that's time domain right there. Got me on that, class? You remember this. I'm not going to prove it right now, but if you do a second derivative, now just try me on this one. If we look at this as the transform of the first derivative, right? Just you could call this a new function. You could call this like y of t. And therefore, if I wanted to transform a dy dt, then all I do is say, well, if I know I'm calling this y of t, that's a transform. dy dt would be, then you would go ahead and just take this as your y of s, and you would then put s times y of s minus the actual evaluation of the derivative of y with respect to t at 0. Let me just write it out for you. So this becomes simply s squared, x of s, and then it's going to be plus s times x, and this is t equals 0 minus. And then it's going to be plus, and this would be dx dt at t equals 0 minus. And you can look at the book. They have a general expression for any ordered derivative. Practically speaking, second order is about as high as you get usually. And the thing about it is, these values you would term in your circuits courses, the x of 0 would be the initial condition. It could be a voltage on a capacitor or current in an inductor. And you remember doing those problems with transients, right? Where you had initial conditions. So that's time derivative. Then, you were trying to get to your problem, and I hope I have time. Integration, that's yours. That's the one you want. Let me put it here. So then, the next one is, if I have, again, we assume the x of t goes to x of s, knowledge. Now if I have the integral, I can't use t here, so I'll use tau d tau from 0 to t. It's really the integration of x of t. Before we did differentiation. This is the opposite, it's integration. And we want to know what happens here. Well, come over and use the fundamental definition of the integral from 0 to infinity of that, the integral from 0 to t of x of tau times d tau, and then we take times e to the minus st dt as such. I think I've got everything right. Yeah, now the order was this, right? But what you can do is change the order of operations, and you can do, well, let me try to explain this. I'll tell you what. You've got about 15 minutes. I got to get you a quiz, but this one right here, the integration will go to simply x of s over s. And the way it happens here is going to be by an integration by parts. And I got to tell you that this becomes the u, and this becomes the e to the minus st dt becomes the differential. And then when you do that integration by parts, you're going to get that right there. And I'll tell you why. Because when you take this and integrate it, you're going to get a 1 over s. You follow me on that, class? That's the part. I don't have time for that. I got a quiz for you. So would you do me a favor, take everything off your desk? Huh?
I thought last week you mentioned that we would have 2 quizzes next week and no quiz this week.
Because we only had the one class.
All right. All right. You got me. You're right. I have it made out. We won't have a quiz today. We'll have it on Monday. All right. And I thought, didn't I put something up that it was going to be on discrete time convolution?
Yeah. So.
All right. Monday's quiz I'm going to make on Laplace transform, so you do your homework. All right. And I got this quiz here. I'm not hand it out to you just to show you the order of difficulty. It's a simple one. I'm just going to give it to you. All right. So just take one, pass it around. Start over here.
Can you take it? Hold on.
That's all right.
You're going to kick yourself for not taking it.
Oh,
Oh, God.
no.
Here's a gimme.
Can we change your answer?
I'm going to do some more. Just give me a second.
Oh, this is.
By the way, is anybody following along in the book about these properties? Does anybody have a book? You got a book? What page is the integration one on? Huh?
I didn't bring it with me. I got it.
Oh, your book?
I didn't bring it with me. I was just following along.
Do you have a book here? You got a book. Here, here's mine. This is in the book. I'm really showing you stuff that's in a book. Would you do me a favor when you guys just find out where it is, where the integration, when you have the integral of x of t, not the actual table, but the proof for it, because it's a straightforward proof. If you want me to do it, I'll do it. I guess I have time now.
Dr. Baginski, what does that mean if multiple numbers have a line under them?
It's wrong. No, the 0 should be just on the first one of that.
Okay.
It's on the first one in both. Oh, that shouldn't have a line. It should be the very first, I think one was like 1 0 1 0 and the other was 1 2 3 4 and something, but they have, the 0 is on the very first number in both of them, it's supposed to. But that's a simple quiz. Yeah, she's doing it right. How can we be so dumb? Well, it was a simple quiz. Don't worry about that. The one on Monday will be simple if you do your homework, all right? So now, let me just finish up this integral one. So we had this. It's the integral from 0 to infinity, right? Of the integral from 0 to t of x of tau d tau times st dt. What page is it on?
It's 93, and it kind of like crosses over in 94.
Yeah, does it use integration by parts or not?
Yeah, they do.
It's easier with integration by parts. We call this part, we're going to call u equal to the integral from 0 to t x of tau d tau, and then we call dv here equal to e to the minus st dt. And the reason is because I know I need a derivative of that. I got an integral, a derivative just gives me x of t, right? Mm-hmm. So when I look at this, then we have du here is simply equal to x of t, and the integral of this, the integral of v, of dv becomes minus 1 over s e to the minus st, and that would be simply v, correct? So this is equal to, first I put the differential down, so it's the differential of uv, the differential of, and then it's going to be this times v, which is going to be minus 1 over s times e to the minus st, and that is a differential, minus, and v, which is going to make it a plus, so it's uv, yeah, minus makes this a plus 1 over s times x of t times e to the minus st, and then we've got to integrate both of these, so then I integrate that from 0 to infinity, and integrate that from 0 to infinity, and I can see that the last one is 1 over s times the very definition of x of s. Let me just point this out to you. The 1 over s comes up in front because the integration, you can put it there as a t. Now when I have x of t e to the minus st dt, that is x of s. Do y'all see that? With me? Now this part over here, let me say that when I do the integration, it ends up being this, from 0 to t, x of tau, e to the minus st right there, minus sign, this is d tau, and this will go away. I'm not quite seeing it right there, but this one goes away. In the book, he's going to make an argument for the range of this one, and I think it goes from 0 minus actually, because it is a differential to 0 plus. Does he, what page is that on again?
Page 93 right here.
93 to 94. The step that you're on is 94.
Oh, I see. Let me explain it right here. This integration, I didn't put it down very well. Here's what happens. When I do this, I'm left with this right here, and it's evaluated from 0 to infinity. At infinity, this gets it away. At 0, all right, at 0, because this is an integral, when you integrate a function from 0 to 0, it is still 0. And this part goes away. And the thing to take from that is this, that the actual transform of the integral of x of tau, d tau, from 0 to t is this. And there is no second term at all because of that. Now, the next thing, I got that. Oh, I want to mention, I'm going to try to mention two things that I feel are important. Like, we've done differentiation, integration, right? Those are common things you see, correct, class? Another thing you commonly see is this. T times x of t, that's the first one, or x of t over t, that's the second one. You're always going to see that appearing. Now, when we do tx of t and we come over here, I'll tell you how you always think about these things. Anytime you have a multiplication by the argument of the function in one domain, think about the derivative in the second domain with respect to s. Now, let me show you why I'm saying that. And if it was vice versa, if they had a derivative in the, or I should say, if it was s times x of s in the frequency domain, always think of a derivative of x of t in the time domain. What we just proved that. I'll get to this in a second. What it means is when you multiply by a variable, that's what really is the domain's variable, like either S or T, in one domain, it always is going to be a derivative in the other domain with respect to the variable that's in that domain. So here, if I have x of s is equal to the integral from 0 to infinity of x of t times e to the minus st dt. Now just watch, and you'll see this real clearly. You all agree that's right? That's fundamental. I'm going to take a derivative of both sides right here with respect to s. So when I take a derivative of x of s with respect to s, well, what do I get? S is there. I end up with what? Minus t, right? Still the integral from 0 to infinity. I get minus t times x of t times e to the minus st dt. You all see that, class? With me? Right? Just the derivative with respect to s. Now, keep looking. What happens? I can take and multiply both sides by a minus 1. And now, what do I have? I don't have the Laplace transform of x of t e to the minus st dt. I have the Laplace transform of tx of t. So it assumes if you know this pair, then if I multiply that by t, I can get that. And I'm going to do you an example so you see it. I don't mean to be talking so fast. I had 3 other things I wanted to do, and I'm not going to get to all of them, but I want to show you. So just watch. Let's do it this way. X of t is going to be equal to e to the minus 10t u of t. I want to do one that's specific, all right? Now, I know that the Fourier transform of that, this is one you should know, is 1 over 10 plus s. Does everybody agree with me there? How many remember that one? All right, most of you should, because you've had Laplace transforms. This is one I proved to you. It was in the homework too, wasn't it? I mean, this is extremely common, and one you have to have at your fingertips. Now, what happens, this is my x of s. What happens if I put t times x of t here? Well, the property would be, and I didn't write it down over here, that's just equal to minus derivative of x of s with respect to s, right? So what do? I mean, I could do this integral by parts. I mean, this is an integration by parts when you have t e to the minus 10t u of t, right? dt times e to the minus st. That's an integration by parts. I could, and I call it brute forcing it because there's more work involved. The simple way is just take a derivative of that and put a minus sign. So I say it's minus the derivative of this. That's 1 over 10 plus s squared, right? Times the derivative of this with respect to s is 1. So that's what it is. If x of t is e to the minus 10t u of t, and I know that transform pair, I know the transform of that is 1 over 10 plus s, right? Then if I say I want the transform of tx of t, or really the transform of what? T times e to the minus 10t u of t, that's the function, right? Y'all see it? Then the only thing I do is take a derivative of that, and bang, it's right there. And put a minus sign, gotta put a minus sign. So that's multiplication. You wanna take a guess what happens when we do 1 over t? If one of them is a derivative, what do you think the other is gonna be? Integral, that's right. You can more or less see this. So for this one, is this property in your book, by the way? I don't know if it is. It is. There's a couple that aren't now. I'll put them there. Well, then for this one, it's going to be the integration. So, by the way, are you guys using those videos? I mean, they're up. How many have? Anybody, any problems with them? Now, they got a way to actually post, I haven't looked there in days, and post comments and questions, don't you? Like over this weekend, you're gonna have time to study. I can encourage you to interact. You'll find it an incredible study guide. I mean, it helped you. If you don't understand something, believe me, people probably do, and they'll post it. And I may take a look or two, especially if I get pinged a bunch by people. And I'll just post it there. Because to be frank about it, things like that that's your world these days, right? You live in the social media world, it's the group me and probably others. So use it. Yes?
I have a dumb question.
There's no dumb questions here.
The x of t that you just did with the, initially it was 1 over 10 plus s.
No, it was e to the minus 10t u of t.
I'm saying the answer.
Laplace transform.
The
Oh,
transform.
the Laplace transform is minus 1 over s plus a, or 10 squared, right?
So when you did just x of t, the Laplace of e to the negative 10t.
U of t is 1 over s plus a.
Yeah. So if you took the derivative of that, wouldn't it be the natural log?
That'd be integral, wouldn't it? Integral of 1 over x, right?
Okay.
All right. It's all right. Don't worry about that. So coming back to this one, let's go take a. Am I out? Somebody has to go over to Parker. Or where are you going? Listen, I'm sorry. The thing about this is just write the definition of Laplace transform. All right. Look at the definition. Instead of a derivative, take an integral of x of s. All right? And you'll find the form of the 1 over t. Got me on that, class? Yes, I'll do your problem.
No, just a quick question. So if you have t squared x of t, would that be the second
Here's
derivative?
what you do. If you start out with this, if you want t squared x of t, you start with first x of t goes to here, right? Got me? Goes to x of s. Then you take a derivative. Now you have tx of t, right? Let this be a new function, y of t. Now take t times y of t. And now you're going to take a derivative of this.
Okay,
All right?
okay.
But you can see the progression. And by the way, this takes time too. In my opinion, because you've been exposed to Laplace transforms once, they're not nearly as bad as convolution. But they take work, and you're going to have to know your properties. Now, I'll answer yours upstairs if you have time.
I have a meeting soon.
All right, I won't answer yours. But if you want an answer, stop back, and we'll do it. You were ready for that quiz. That wasn't a hard one. It was a trivia quiz.
Can I
Please, can I rethink my answer?
Oh, I'm good.
I had other things to do.
Right.
I was not able to do them. So I'm gonna do it today. I'm gonna do it all